In this video, we are going to talk about limit. Let's begin with some history. In the 1600s, French mathematician Pierre de Fermat was working on a problem that looked like this. He was trying to find the slope of a line that is tangent to this curve. But what he knows is this slope formula. We can find the slope of a line by getting the ratio of the chains in y over the chains in x. This color pink line is what we call as a secant line. A secant line intersects the curve at 2 points. We have this one point of intersection and we have this other point of intersection. And so if we want to get the slope of this pink line, which is a secant line to this curve, we can simply subtract 4 and 1 to get positive 3 and subtract 2 minus 1 to get positive 1. So therefore, the slope of this secant line is positive 3. But what Pierre de Fermat wants is to find the slope of the line that is tangent to the curve. And when we say tangent to the curve, there must only be one point of intersection between the curve and that line. So this red line could be the tangent line. And there's only one point of intersection here. But there's a problem getting the slope of this line because we only know one point. And if you're going to use the formula for the slope, then you will have y sub 2 and y sub 1 equal to itself. And therefore, you will have 0 over the chains in x is also 0. And you get an indeterminate form. And division by 0 is undefined. So this formula will not work if there is only one point. And therefore, you cannot get the slope of this line that is tangent to the curve. So what Pierre de Fermat did was to think of a very small, non-zero, but almost zero quantity, and he called that quantity as E. So if our particular specific x value is, let's say, this value, x here, he imagined a very small quantity that is so close to x, and this interval here is of magnitude E, where E is a very, very small number. So you now have 2 points here. One is x, and the other is x plus E. So you can now think of E as this point, and there's a corresponding y value. So at our input x, there is a corresponding y value, which is f of x. And f of x is this point. And at input equals x plus E, this point now has a coordinate x plus E, this point. At input equals x plus E, then there's a corresponding y value, which is f of x plus E. So, if I now think of these 2 points, then this formula for slope will now be applicable because we now have y sub 2 equals to f of x plus E, which is now this expression, and our y sub 1 is this point, which is now this expression, f of x, and we copy the minus sign. For the chains in x, our x sub 2 would be this point, which is x plus E, which is now this point, and our x sub 1 would be this point, which is denoted by x. We have this x. So basically, this formula computes for the slope. And then simplifying, Pierre de Fermat arrived at this value, 2x plus E. But going back to the definition of E, E is a non-zero, but almost zero quantity. So this value is close to 0. Its magnitude is almost negligible, such that this 2x plus E is basically 2x. And therefore, Pierre de Fermat now concludes that the slope of the line tangent to the point at x is now computed using the formula 2x. What does this mean? If our x is 2, what does this mean? At point 24, that means x equals 2, the slope is 2 times 2 because you have 2x, so this becomes 2 times 2. The slope of the line tangent to this point has a slope is positive 4. So the tangent line here has a slope of positive 4. If you take a point, let's say negative 2, 4. The x value here is negative 2 and the y is 4. What is the slope of the line tangent to this point? Then using again the formula 2 times negative 2, we get a slope of negative 4. And so you now have this line. This is the line tangent to the curve at this point. And this tangent line has a slope of negative 4, which is correct because the line is going downward. Of course, the slope is negative. While here, the line is going up and the slope is positive. At this point, which has a coordinate of negative 1, positive 2, what is the slope of the line that is tangent to that point? we can compute using this formula 2x. 2 times the x value -1 equals -2. So therefore, at the point -1, 2, the slope of the line tangent to that curve at that point is -2. How about the slope at this point of origin? The coordinate here is 0, 0. That means x is 0. So 2 times 0 is 0. That means the slope of the line at the point of origin is 0, and that is a horizontal line. This concept of finding the slope of the line tangent to the curve is very, very powerful, because for the slope of the secant line, you can think of the slope of the secant line as the average rate of change between 2 points. But the slope of the tangent line would be the instantaneous rate of change of the curve at that instant. So at any point here on the curve, you can find the rate of change. And those changes are varying for every value of x. And because of this concept, we now open the door to study the mathematics of change, because we can now compute the rate of change at any instant in the graph. And that branch of mathematics that deals with the mathematics of change is now what we call as calculus. So Pierre de Fermat and other mathematicians open up the door to the branch of mathematics that we now call as calculus. Later on in the 17th century, English mathematician Sir Isaac Newton and German mathematician Leibniz are often credited to be the founders of calculus based on their work in the late 17th century. But the fundamental theorems of calculus, derivatives, and many other parts of calculus predated them. They built their calculus on the mathematics of their predecessors, such as Pierre de Fermat. And in particular, Sir Isaac Newton's approach to derivatives followed that of Pierre de Fermat, but he uses limits instead of imagining E. While Leibniz's approach was to use infinitesimals, or positive quantities that are smaller than any positive numbers, which is similar to the value of E as imagined by Pierre de Fermat. So we mentioned here the word limit. For many mathematicians during that time, they were looking for a foundation that will become the basis for that very small number E as imagined by Pierre de Fermat. And 200 years later after Fermat, German mathematician Weierstrass and Bohemian mathematician Bolzano were credited with providing a rigorous footing for calculus in the form of the modern epsilon delta definition of limit. And this is now the rigorous definition of limit. But when I was first studying this definition of limit, I find this so abstract, and unless we have an intuitive understanding of what limit is, you will find this definition so abstract. So let's talk first about the informal definition of limit. An informal, intuitive definition of limit is that a function f, our function f is this curve, approaches the limit L near A. What does this mean? The limit L is the y value. You can think of L as this point. And A is an x value. You can think of A as this point. So we can now think of this sentence. A function f approaches a limit L near A if we can make f of x as close as we like to L. So first, where are the x values? The x values are the values in the horizontal axis. And if you have a specific value x here, then there is a corresponding y value here, which we call as f of x. If you want to make f of x, this is f of x, sufficiently close to the limit L, that means this distance is very, very small, this distance, then we can achieve that by requiring that our x is here, this point, approaches a specific value A. So we make this x so close to A, but not equal to A. And so by making this x close to A, we can have this value. And our f of x is becoming closer and closer to the limit L. So we can now write this idea in this way. The limit of the function is the curve. The limit of that function as the input approaches A is this x value, is the limit L. Let's have some examples so you can understand this. Let's say you have this question. What is the value of the function x squared minus 1 over x minus 1 at x equals 1? So what we can do is just substitute directly the value of x to the function. So computing now for f of 1, we now have 1 squared minus 1 over 1 minus 1, which is 0 over 0, which is indeterminate. And division by 0 is also undefined. So we have a problem here. F of 1 is not defined. So we now say f of 1 is undefined. Now, what if instead of evaluating the function at x equals 1, we just take values of x that are closer to 1? Let's say x is 0.5, 0.9, 0.99, or take any value that is closer and closer to 1. Here is our result. At x equals 0.5, y is 1.5. Let's plot those points. At x equals 1/2, f of x is 1.5. At x equals 0.9, so you are now close to 1 at this point, then the y value is 1.9. So you now have these points. And as you go closer and closer to 1, then the y value becomes closer and closer to 2 also. But at exactly 1, the function is undefined. This is the behavior of the function as we take x values from the left going to the right. So 0.5 is coming from the left and 0.999 is going to the right. Our direction is going that way. Now this time, let's take values coming from the right side. So what if x is 1.5? X 1.5 is here. The value of y is 2.5. This is 2.5. If x is 1.1, that is, we are now closer to 1 at this point, the y value is 2.1. And then we go even closer to 1. At 1.01, the y value is 2.02. And at 1.00001, the y value is 2.00001. So this value is now very, very close to 2. Let's take those two observations where our x value is coming from the left and coming from the right towards x equals 1 in the next slide. So this is now what we got. We have coming from the left, the limiting value is 2. Coming from the right, the limiting value is also 2. Now these values in the table, as we take values of x closer to 1, and we approach a limiting value, can now be written in limit notation like this. We can now write the limit of the function x squared minus 1 over x minus 1 as x approaches 1 from the left. Notice this small minus sign, and the limit is equal to 2. This other graph, where we approach x from the right, can now be written this way. The limit of the function x squared minus 1 over x minus 1 as x approaches 1 coming from the right. Notice this small plus sign to indicate the direction is coming from the right, and the limiting value is the number 2. I want you to notice this. X approaches 1 raised to negative 1. This read as x approaches positive 1 coming from the left. And this notation is read as x approaches positive 1 from the right. And the limit here is 2. The limit here is 2. If you have this notation, x approaches 1, and you don't have this small minus sign nor this small plus sign, this is called as a two-sided limit. Whereas this one is called as a one-sided limit, and this other one at the right is called as a one-sided limit. And this limit at the middle is what we call as the two-sided limit. And the two-sided limit exists if both the left-hand side limit and the right-hand side limit exist. In our case, our left-hand limit is positive 2 and the right-hand limit is positive 2. So we now say that the two-sided limit is also positive 2. If, on the other hand, this value is different than that value, then the two-sided limit does not exist. Another important thing for you to consider here is that the value of the function at x equals 1, that is at f of 1, was computed as undefined in our previous computation. So even if at x equals 1, the function is undefined, we are not interested at the exact value of the function at f of 1. We are only interested at the value of y as x approaches that instant of x. So may I repeat this? In our computation of the limit, it doesn't matter whether the function is defined at the specific x value. What we are after is the value of the y as x approaches that specific x value. So limit is a special way of saying ignore what happens when we get there. But as we get closer and closer to 1, the answer gets closer and closer to the limiting value, which is 2. So the limit is the value as we get closer and closer to the specific x value. That distinction is very important because some functions are discontinuous. When a function is not continuous, the limit may still exist at that point of discontinuity, which we are going to look at in our next example. Now let's consider this greatest integer function. Consider this function f of x is equal to the greatest integer function of x. Let's take any x value. Let's say x equals 0.1. What is the greatest integer before 0.1? And the answer is 0. So therefore, at x equals 0.1, y is 0. Take any value, let's say 0.5. What is the greatest integer before 0.5? And that is 0 again. But at x equals 1.1, what is the greatest integer before 1.1? That is 1. In other words, you are just getting the floor. You are rounding down this integer. So that if you have 2.7, if you round this down to the nearest integer, that integer is positive 2. And so we now have this graph of the greatest integer function. And the greatest integer function is discontinuous. Now, what is the limit of this greatest integer function as x approaches 1 from the left? So let's identify x equals 1. X equals 1 is this point. If we approach 1 from the left, the direction is going this way. What is the limiting value? The y value would be 0. So the limit here is 0. The limit of the greatest integer function x as x approaches 1 from the right, so we are going this way, and approaching 1 from the right, so 1 is this point, we now have this particular y value, which is 1. So the limit here is 1. Notice that the left-hand limit and the right-hand limits are different. You have 0 and 1. And so, when we remove this little plus sign or minus sign here to indicate one-sided limit, when we now consider the two-sided limit, then the two-sided limit here does not exist because the left and the right-hand limits are not equal. So we now say the two-sided limit does not exist. Now let's talk about removable discontinuity. What is a removable discontinuity? We say that the function is continuous if you can trace the function without lifting your pen or your pencil. But in our example, there is no way for us to trace this function without lifting our pencil or pen at this point. There is a hole. But this hole can be repaired by just plugging in or putting in this one single point to complete all the points in this curve. When all you need is one point to repair the function to make it continuous, then you now say that that function has a removable discontinuity because the discontinuity was created by just removing a single point, and it can be repaired by putting that point back to the curve. So what is the limit of this function, a piecewise function, x squared plus 8x plus 16, when x is not equal to 3, or the function is equal to 3 if x equals negative 3? So let's take a look at the left-hand limit. So as x approaches negative 3 from the left, we are coming from here, going this way. What is the y value? The y value is the limit. So the y value is approaching positive 1. So the limit here is positive 1. Let's take the right-hand limit. As x approaches negative 3 from the right, so we are going this way. And what are the y value? The y value are these points. And as we get closer and closer to x equals negative 3, the y value is approaching also positive 1. So the limit is positive 1. Since both the left and the right-hand limits are the same, then the two-sided limit exists, and that is also equal to the same values here of 1. Now, what is the value of f of negative 3? If x equals negative 3, then the value of the function is 3. So therefore, f of negative 3 is positive 3. Notice now that the left-hand limit is positive 1, the right-hand limit is positive 1, the limit exists and is also equal to 1, even though f of negative 3 is not the same as these limits. Because in the limit, we are interested in the values as x approaches that specific x value. But we are not after the exact value of the function at f of negative 3 in this case. So that's the difference between just evaluating a function and evaluating a limit. In algebra, most of the time, we are interested in getting the y value for any particular input x. But in limit, we are only interested in the y values as the input x approaches the point of interest. Now let's talk about limit at infinity. Let's consider this rational function. This is the parent function of rational functions. The limit of 1 over x as x approaches infinity. So where are the x values? The x values are our horizontal values. And our x values are approaching infinity. So we're going that way. What is the y value as x approaches infinity? Notice from the graph that as x becomes larger and larger, the y value is approaching the number 0. So we now say the limit here is 0. We do not have the left hand and the right hand limit here because we are going to the right side infinity, and we do not know what is to the right of infinity. So in this case, we are able to find the limit at infinity. Even if the question is x approaches infinity, we are able to describe the y value because the pattern is that this x-axis is the asymptote of this rational function. If we have limit at infinity, there is also what we call as limit to infinity. Let's take a look at an example. So we have here limit to infinity. What is the limit of the function 1 over x squared as x approaches 0? So we are going to look at both the left hand and the right hand limits here. If we're going to look at the left hand limit as x approaches 0 from the left, what is the limiting y value? Notice that the y value gets larger and larger, and we now say that the limit at the left is positive infinity. If you are coming from the right, what is the limit of the function as x approaches 0 from the right? Notice also that the y value is getting higher and higher to positive infinity. So the left hand and the right hand limits are the same, so the two-sided limit exists, and that is equal to infinity. So at x is getting closer and closer to 0, the y value is going to infinity. Now let's talk about essential discontinuity. In the previous example, we talked about removable discontinuity. In here, we're going to talk about essential discontinuity. An essential discontinuity is a discontinuity that cannot be repaired by just plugging in a single point. For example, in this function, you cannot repair the discontinuity by just using a single point because you have this wide open discontinuity. Now, what is the limit of this function? We can identify it by looking at the left hand and the right hand limit. So let's take a look now at what is the limit of this function as x approaches negative 2 from the left. So this is negative 2. We now write the limit of the function 3x over x plus 2 as x approaches negative 2 from the left is that y value. What is the y value as we get close? What is the y value as we get closer and closer to negative 2? So the y value here is positive infinity. On the other hand, if we approach from the right going to negative 2, what is the y value? The y values are these points, and that's going to negative infinity. So we now say that the limit of 3x over x plus 2 as x approaches negative 2 from the right is negative infinity. Now, since the left hand and the right hand limits do not agree, one is going to positive infinity and the other is going to negative infinity, then we now say that the limit of this function does not exist. Let's take another example. What is the limit of this rational function as x approaches negative 2 from the left? So we are after the one-sided limit in this question. So where is negative 2? Negative 2 is this point. As x approaches negative 2 from the left, so the left side is here, the y value, these y values, are approaching y equals negative 1. So therefore, the limit of this function is negative 1. I use this problem because sometimes when you look at the graph, you automatically assume that you are going to get the limit at the point of discontinuity. You always pay attention to whatever is the specific x value that you are approaching to. In this case, we are approaching negative 2. And this part is just a distractor, something to distract you if you are really analyzing the question. And you'll notice here also that for removable discontinuity, oftentimes you can find the two-sided limit. And for essential discontinuity, sometimes you can find the two-sided limit, sometimes you can't find the two-sided limit. When we say we are going to evaluate the limits, what we want to do is we want to compute. We want to find the value of the limit. So let's have some examples. Let's say this is our problem. Find the limit as x approaches negative 3 of this irrational function. The first thing that we're going to do is try substitution method. If the substitution method works, that implies that the function is continuous at x equals negative 3. So let's substitute now negative 3 for the values of x. So we have here negative 3 squared plus this x becomes negative 3 and minus 12. In the denominator, we are going to substitute negative 3 for this x to get negative 3 plus 4. And so, by direct substitution, you have this negative sign. Negative 3 raised to the second power is positive 9. You have here minus 3 minus 12 over negative 3 plus 4 is positive 1. And so you have 9 minus 3 is 6. 6 minus 12 is negative 6. And then you have this negative. So you have negative of negative 6 over 1, which is positive 6. So the limit of this rational function as x approaches negative 3 is positive 6. And we arrive at this answer by just substituting directly the value of whatever is the number here to x. Now, not all the time direct substitution works. For example, if we're going to use substitution method here, this is what we're going to get. This x, this becomes 1 squared plus 1 minus 2 over 1 minus 1. And what is the value? 1 squared is 1, plus 1 is 2, minus 2 is 0, and 1 minus 1 is 0. So you have an indeterminate form. If you already know derivative, when you have indeterminate form like this, then you can use the L'Hopital rule. But we are still in limit, so in the absence of knowledge about derivative, we cannot use that L'Hopital rule, and we cannot use also direct substitution. So the other method that we can use here is what we call as factoring. We use the factoring method if the direct substitution will not work. So what we have now is the limit as x approaches 1 of the factors of the numerator over x minus 1, provided x minus 1 is not equal to 0 or x not equal to 1. This is not a problem here because we are only approaching 1. We are not getting f of 1. So how do we factor now this quadratic trinomial? What we are going to do is get the coefficients of the first and the last term. That is 1 times negative 2 is negative 2, and the coefficient of the middle term is 1. What are the factors of negative 2 that will resolve to 1 when added? Those numbers are 2 and negative 1. If you multiply, you get negative 2. If we add, we get positive 1. So the factors now are these two numbers. So we have x plus 2 and x minus 1. Notice now that x minus 1 and x minus 1 are common factors. So what we can do is we can cancel this out, and what we have is the limit as x approaches 1 of x plus 2. And if we are going to substitute now positive 1 to x, what we have is the limit of this is positive 3. So we are able to find the limit by first doing the factoring method, canceling out the common factors, and substituting the value of x in the simplified form of the rational function. So the limit is positive 3. Now let's have another situation. Find the limit as x approaches 4 of 2 minus the square root of x over 4 minus x. Again, if you're going to use direct substitution, you'll have 2 minus the square root of 4 over 4 minus 4. And that gives us 2 minus 2 over 4 minus 4, which is also 0. So you have the indeterminate form 0 over 0. So direct substitution will not work here. If we're going to use the factoring method, there is no way for us to factor this. So instead of factoring, what we are going to do is we are going to multiply this by the conjugate. What is the conjugate? The conjugate of a plus b is a minus b. So the conjugate of 2 minus the square root of x is 2 plus the square root of x. Now, if you multiply the numerator by 2 plus the square root of x, you are going to multiply also the denominator by the same factor, so that this 2 plus square root of x divided by itself is 1. In effect, the value that you are multiplying to the given function is 1. And by multiplying by 1, you are not changing the value of the function. You are just changing its form. So let's simplify this now. So what we have is the limit as x approaches 4 of the simplified form of this function. So what we have here now is a special product, the sum and difference of two numbers, which we can simplify as difference of two squares. So what we have is the square of 2, which is 4, minus the square root of x is x. And then we copy 4 minus x and 2 plus square root of x. Now 4 minus x is a common factor, so we can cancel this out with the condition that 4 minus x is not equal to 0, or x is not equal to 4. And so what we have is the limit as x approaches 4 of 1 over 2 plus the square root of x as x approaches 4. So what we have now is the limit as x approaches 4 of 1 over 2 plus the square root of x, because this is now cancelled out. So let's continue here. By direct substitution now, if we substitute 4 to x, what we have now is 1 over 2 plus the square root of 4. We substituted this 4 into x. And this value is equal to 1 over 2 plus the principal square root of 4 is 2. So what we have is 1 over 4. So the limit of this function is 1 over 4. And we computed this by multiplying the numerator in the denominator by the conjugate of the numerator. In the other video, we already talked about the sandwich theorem, and we're going to apply that here. So if you haven't watched our video on the sandwich and the squeeze theorem, then I encourage you to watch that video so you can understand what we're going to do here. So what is the limit as x approaches infinity of sine x over x? So to solve this problem, we're going to recall the graph of a sine function. Now for the graph of the sine of an angle, the graph has an amplitude of the absolute value of 1. That means the range of values that the sine of an angle can take is from -1 up to +1. So the amplitude is absolute value of 1. We can use the same observation to write now this inequality. We can now say that the range of value of sine of x is from -1 up to +1. Since the form that we want is sine of x over x, we can divide each term here by x. As long as x is greater than 0, then that is a valid operation. We are not going to change the inequality symbol. And we know that x is a positive number because x is approaching positive infinity. So this inequality is valid. And then we'll get the limit of -1 over x as x approaches positive infinity less than or equal to the limit of the middle sine of x over x as x approaches positive infinity less than or equal to the limit of 1 over x, this part, as x approaches positive infinity. So what I did is I get the limit of each of this one. The limit of this, the limit of the middle, and the limit of the right. So what is the limit of -1 over x as x approaches positive infinity? So you have the number -1, and you divide that by a very, very large number. So this limit would become 0. And we do not know the limit of this, so let's just copy the limit of sine of x over x as x approaches positive infinity. Less than or equal to, what we have here is 1 divided by a number that is very, very big. And so the limit of this would result also to 0, because 1 divided by a very, very big number is approaching to 0. So this middle expression now is sandwiched by two values that are equal to 0. From the sandwich or the squeezed theorem, we can conclude that this middle expression must be also equal to 0, because the left side is 0 and the right side is 0, and these two values are squeezing this middle function. And so we now conclude that the limit of sine of x over x is also 0. So the value of this limit is 0. Now let's try this problem. What is the limit as x approaches positive infinity of 5x plus sine x all over x? Another technique that we can use is to use the properties of limits. And we have the list of these properties. The first one is the limit of the sum of two functions is equal to the sum of their limits. In other words, you get the limit of the first function, get the limit of the second function, and you add those two limits. We call that as the sum rule. Then we also have here the difference rule, the constant multiple rule, which says that if you have a constant times a function, you can put that constant out and get the limit of the function and multiply that constant times the limit. Then we have the product rule here, and then we have the quotient rule, the power rule, and the root rule. What we're going to do is we're going to use these properties of limit or the limit laws in order to re-express this 5x plus sine x over x. So what will happen here is we'll have the limit as x approaches infinity, and then we're going to split this into two terms. We have 5x over x plus sine of x over x. So what we did is we divide each of these terms by x. Now this form is similar now in form as the sum rule, where 5x over x is our f of x, sine x over x is our g of x. And the sum rule says we can get the individual limits of each of these terms, and the limit of each of these terms becomes the sum of the limit. So the limit of the sum is equal to the sum of the limits. But 5x over x is just 5, so we can simplify this as 5. And so we now have the limit as x approaches infinity of 5 plus the limit of sine of x over x, where x is approaching positive infinity. And so we split now these two into two limits, which is exactly what the sum rule is saying. So what is the limit of 5 as x approaches positive infinity? Since there's no variable here, no matter what values x assume, this constant is not affected, so the limit here is 5. And the limit of sine of x over x as x approaches infinity, we already computed in the previous example. We know that the limit of this is 0. And therefore, the limit now of this entire function is 5 plus 0, which is equal to 5. So the answer here is 5. Let's have another example. Let's say you have the limit of sine of x over 2x squared plus x as x approaches infinity. What we can do here is we can simplify this denominator. There's a common factor of x, so we can write 2x squared plus x as x times 2x plus 1. So therefore, we can now write this as the limit as x approaches infinity of sine of x over x times 2x plus 1. Now, using now the product rule, we can express this as the limit of the product, and the limit of the product becomes the product of the limits. So let's write this as the limit as x approaches infinity, and then we now have sine of x over x. So we take this sine of x over this x times 1 over 2x plus 1. If you multiply these two, you will go back to this previous term. What this enables us to do is to split these two factors into two separate limits using the product rule. We can now have the limit of sine of x over x as x approaches infinity multiplied by the limit of 1 over 2x plus 1 as x approaches infinity. The limit of sine of x over x as x approaches infinity, we already computed before. We know that the value of this limit is 0 times. Now, even if you do not compute this, if you have 0 times any number, the result is still 0. But we can still also compute this. What is the limit of 1 over 2x plus 1 as x approaches infinity? Notice that if x is going to infinity, this 2x becomes a very big number. So 1 divided by a very large number is 0. So the limit here is also 0. And 0 times 0 is 0. Therefore, the limit here is 0. And we do this by applying the product rule and using the previous value that we arrived at for the limit of sine of x over x as x approaches infinity. So these are some of the techniques that you can use when you evaluate limit. Let's have another example. Find the limit of x sine of x plus 2 sine of x all over 2x squared. So using again the sum rule, we can split this into two addends. So we can have the limit as x approaches infinity of x sine of x over 2x squared plus the limit as x approaches infinity of 2 sine of x over 2x squared. And this x in this x squared can be simplified here as sine x over 2x. So you have the limit as x approaches infinity of sine of x over 2x, which we can also simplify by writing it as 1/2 times sine of x over x. And in here, we can cancel out the 2, and so we can write this as the limit as x approaches infinity of 1 over x times sine of x over x. So this x squared is split as this, and then you have sine x at the top. Now here you have a constant multiple, which we can write by writing outside. So you have 1/2 times the limit as x approaches infinity of sine of x over x, which we already know the value, plus this part, we can find the limit by applying the product rule. So we can split this into two products. The limit as x approaches infinity of 1 over x times the limit of sine of x over x as x approaches infinity. So this second term is now split into two factors by applying the product rule. And so what we have now here is 1/2 times the limit of sine of x over x. What's the limit of sine of x over x as x approaches infinity? We know this value is 0. So 0 times 1/2 will give us 0. And what is the limit of this? As x becomes bigger and bigger, 1 over x is also approaching 0. So this part here is 0. And we know the value of the limit of sine of x over x as x approaches infinity. That's also 0. So therefore, the limit of this function is 0. Now let's try this one. What is the limit as x approaches pi over 6 of negative 2 cosine of 2x? As always, the first line of defense is try the substitution method. If we try substitution method, this becomes negative 2 cosine of 2 times x is pi over 6, which is equal to negative 2 cosine of pi over 3. So what's the value of cosine of pi over 3? If you're going to recall the unit circle, pi over 3 is this part. This is pi over 3 here. In degree measure, that's 60 degrees. If you have a 60, 30 right triangle, opposite 30 is 1/2. Opposite 60 is square root of 3 over 2. And the hypotenuse is 1. So cosine is your adjacent side over the hypotenuse. So you get 1/2 over 1. So cosine of pi over 3 is 1/2. So this becomes negative 2 times cosine of pi over 3, which is 1/2 over 1, or 1/2. And therefore, by substitution method, we arrive at a value that is equal to negative 1. So the limit of negative 2 cosine of 2x as x approaches pi over 6 is negative 1.